Chris Howe, who will start today to tell us everything you want to know about duality, double geometry, non-geometric colors.
Okay, thanks very much. First of all, a disclaimer. In 3 lectures, I'm not going to tell you everything you want to know about all of those things, but I'm going to introduce some of these ideas, and I'm going to talk about some selected topics as an introduction to some of these things. But to say everything you wanted to know would take probably many more than 3 lectures, or it would also require me to start off without being so introductory. So I'll start by giving an overview of the material I want to talk about and trying to explain the relationships between some of the ideas and their implications. Then I'll talk about T-duality. I won't assume that you know about it, and I will try and explain some of that. And for the experts, I will try and include some of the issues which are perhaps often glossed over in treatments about that. Then I'll talk about certain kinds of non-geometric backgrounds and the kind of signal models which arise in discussing those. And then in the third lecture I'll talk about the double field theory, which is this approach naturally leads to, and it might be thought of as an effective theory which would understand some of these kinds of issues which take us beyond geometry. And if there's time, I'll say something about the relationship between these ideas and what's known as generalized geometry. So let's start by thinking about what we mean by string theory. There are a number of different approaches to string theory, and they all have different advantages and disadvantages. It can be thought of as supergravity theory plus an infinite number of massive fields. That can be treated in terms of first quantized theory of perturbative world sheet dynamics. However, the full theory is rather more exotic and complex than either of these simple viewpoints would give us to understand. And one of the key features that marks out string theory, and one of the things which has played such a dramatic role in trying to unravel some of the structure of string theory, is the so-called duality symmetries. And I'll talk about the simplest of these, T-duality, which is one which arises in the perturbative string, and is one which because it arises in the perturbative string, can be treated rather completely and rather rigorously, unlike some of the generalizations like U-dualities, where one needs to use more implicit approaches. And in these approaches to string theory all have some advantages and some disadvantages. The supergravity limit is very useful for understanding some effective space-time physics, but it misses many of the stringy features. If you regard it as think of it as an infinite set of fields of higher and higher masses, then that picture is good for some purposes, but it misses some of the dualities and some of the structure which arises from the fact that summing up all of these contributions from all these fields has dramatic effects. I mean, for example, if we considered a finite subset of these fields, it would typically give a non-renormalizable theory, a theory with unavoidable ultraviolet divergences. And it's only when you include the full infinite set that some of the miracles of string theory happen and finiteness emerges. The perturbative approach clearly misses some of the non-perturbative structure, misses the non-perturbative structure of the string. Well, I can do a bit better than that by including d-branes in the perturbative string, but this only keeps some of the non-perturbative structure and misses some of the others, some of the rest. So you see some of the structure, but not all of it. There's the matrix model approaches, which we'll hear something about from Mourinho's lectures, where these are an interesting non-perturbative approach, but in this the geometry is hidden or emergent, and so where it has some advantages, it has other disadvantages. And another approach is a string field theory, which is a second quantized approach, where you have a field which represents the probability of finding, which represents represents the possibility of creating a string at a particular loop in space-time. So it's a field theory on loop space. And this is a very useful way of formulating all of the interactions of the theory. And as we'll see, it incorporates some of the duality symmetries. But it also has a number of drawbacks in that, for example, it's rather hard to use, and it's at the moment it's formulated only as an infinite sum of higher and higher order interactions, each defined iteratively, defined inductively. And so each of these is useful for some kinds of problems, but is not useful for other kinds. So each has some limited validity. And typically, what's done is that one tries to extract aspects from some and not use one approach or another to try and look at each individual problem. So it's clear. So it's another way of saying is we don't really know at the fundamental level what string theory is. We know that in some approach, in some regimes, it's well thought of as a determinative theory of relativistic strings. But we also know that there's a lot more to that. That the branes and the non-determinative structure associated with the branes play a crucial role, especially with strong coupling. So closed string field theory, as I mentioned, is a field theory on loop space. If one's looking at quantum mechanics of a particle, one has a wave function psi of x, which represents probability of finding a particle at a particular point x. And for extension of strings, we would have some loop in space-time, x of sigma, and we have a wave function which is a function of these loops. And it's a probability of finding a string lying precisely on this loop. And when one goes over to the field theory, one ends up with relativistic fields which depend on psi, which depend on x and time. And one ends up with the generalization of string field theory has fields which are functionals of of loops in space-time, x of sigma. And these capture some of the exotic and complicated structure of the interacting string. In particular, they give some of the vertices in a very economical form. As I mentioned, it's non-polynomial. So it's only defined iteratively. It has arbitrary, it has interactions of arbitrary order. Defined the nth order interaction is defined in terms of the lower ones. The symmetry structure is rather exotic. It's not a Lie algebra usually, but it's something rather more exotic. And it's not at all, because it's only defined iteratively, it's not at all clear what the underlying structure of the theory. It's like as if we had Einstein's theory given perturbatively as a series of higher and higher order interactions in a perturbative grammaton. And one didn't understand what the Riemannian geometry underlying it was. The whole thing summed up to a beautiful geometric theory. And one of the things one could try and do in this is to try and seek a subsector of this, capturing some of the exotic structure and the duality, which is simple enough to study explicitly. And finding such a structure will be part of the things I'll be trying to get towards in the third lecture. But if we're looking at the conventional strings in a geometric background, the conventional pictures, we have some space-time manifold. Here it's represented by this green donut. And there are background tensor fields given by a background metric, a background field strength for the two-form antisymmetric tensor, a dilaton, and various other fields. And then the fluctuations of all these fields arises about the background, arises certain modes of the string. And so string theory intrinsically treats the background and the fluctuations in a very different way. And the lessons from general relativity tell us that one gains a lot by trying to find a formulation where one treats the background and the fluctuation together as part of a combined background invariant object. And that's the thing which has intrinsic geometric meaning. And yet with a stringy picture, it seems very hard to understand how to do that. And so one of the things is to try and understand some of the natures of the kind of stringy geometry which might emerge from this. It might be something where it's something induced by integrating out the string, or something which is emergent. And one of the features is that some of the dualities which I want to talk about will mix some of the geometric and stringy modes in an intrinsic way, and so hopefully would have some thing to say about these kinds of questions. And one of the issues is in understanding geometry is that one of the key problems in general relativity is the emergence of singularities in black holes or in the beginning of the universe. And one question is what string theory would have to say about that. And this is clearly also intimately related to the question about how one treats the fluctuations about a background and incorporates the background and the fluctuations in the same footing. So the formulation of strings in a background is given by a nonlinear sigma model, and it has the same structure that we heard about in Bacchus's lecture. We have a manifold with given background tensor fields. So H is the curl of the B field occurring here, and these are precisely the terms you heard about earlier. So we have target space coordinates xi, world sheet coordinates sigma and tau. So for the closed string, sigma would be a periodic coordinate going around the loop of the string, and tau would be a proper time. And the fields x or sigma can be thought of as two-dimensional fields on this two-dimensional world sheet, but they also determine the embedding of the string in the target space in the space-time. And requiring, as we heard, conformal invariance of the two-dimensional theory, demanding conformal invariance of this two-dimensional quantum field theory, of the quantum field theory obtained by quantizing this, constrains these background metrics, these background fields. This conformal invariance requires that the beta functions vanish, that we're at a fixed point of the beta functions. And we saw in Bacchus's lecture that when you just have the metric field, we get the condition that from this, the lowest order, that the Ricci tensor vanishes, in other words, Einstein's equation. And the beta functions for all of these equations, all of these fields together give the supergravity field equations, which one might have expected. So that requiring conformal invariance constrains these fields in that way. So given the background field satisfying the beta function equations, or the field equations, determine a conformal field theory. And one question which arises is whether the same conformal field theory could be given by two different sets of background fields. So a familiar case would be in the case where these are related to these by a diffeomorphism. We know that if you've got the same metric, you've got the same manifold with a same Riemannian manifold, two Riemannian manifolds related by a diffeomorphism, then regarded as the same Riemannian manifold. And they're physically equivalent. Similarly, if B and B prime are related by a B field gauge transformation, B is a 2 form, so if they differ by something which is D of a 1 form, then that's a gauge symmetry of the theory, and these would determine the same theory. And in supergravity, that's all there is. Again, it's a few discrete symmetries. These are the symmetries of the field theory, and the only times when these would determine the same physics is they're related by diffeomorphisms of B-field gauge transformations. But in string theory, the same conformal field theory can be determined by two different sets of data if they're related by a T-duality symmetry, and I'll say what that is in a moment. So although they would determine different space-times to be different from the point of view of general relativity or supergravity, they determine the same quantum two-dimensional field theory, and so determine the same string theory background. And so since they give the same physics, these must be regarded as symmetries of the theory. And one of the things I'll be talking about is trying to show why these are symmetries and deriving this in more detail. But the T-duality is a rather remarkable symmetry. It takes a circle of radius r to a circle of radius 1 over r. Or if I was to strictly speaking, if I was to introduce units, there'd be a string length squared occurring here. So if you had a circle which was large compared to the string length, it would take you to a circle which was small compared to the string length. And it exchanges momentum modes on the string and momentum modes on the circle with modes corresponding to strings winding around that circle. So it's exchanging physical degrees of freedom with solitons. It exchanges the original coordinate of the circle of radius r to a new coordinate of circle of radius 1 over r. And so it can be thought of as acting on the doubled circle, or the 2 torus, with coordinates acting on considering of both of those, and that point of view will be important later. That extends to the case where generalizes to the case where we have, instead of one circle, we have a space which has got d circles. So suppose we've got some d torus here, and more generally you can consider the case where we've got this fibers over some base space, some complicated base space. So we've got the manifold locally splits into a product of this with this, of some curved space with the torus, and there'll be a metric and a B field on the fibers, and the metric and the B field on the fibers will be constant over the fibers, but their values will vary depending on the position y on the base space. So that's what we mean by saying that this is fibered over this. And remarkably, the action of T-duality, which forms an infinite discrete group, includes transformations which will mix the metric and the B field. So these are transformations which are rather unfamiliar in conventional physics, because it's mixing fields of different spins, as well as mixing momentum and winding modes on this torus. And it changes the geometry and the topology of this total space. And the way it acts is rather strange. It acts by way of fractional linear transformations, acting on the d by d tensor, which is given by whose symmetric part is the metric, and whose antisymmetric part is the B field. And when restricted to a single circle, this group collapses to just Z2, and it just becomes the transformation which takes R to 1 over R, the radius being encoded in the one-dimensional metric. So one of the things I'll be doing is explaining all this and showing where this comes from. But as part of the overview, I'm trying to summarize some of the structure which arises and how these ideas are related. So the aim of the second lecture will be to talk about the relationship between symmetry and geometry. So usually we're used to thinking about space-time as constructed from local patches. And the symmetries of physics are used in patching together the local patches. So in each local patch we have conventional physics of the laboratory frame. And we glue these together with various symmetries. So one of these is using the reparameterization symmetry. So patching different patches of space-time together with diffeomorphisms is what we use to construct a manifold. If we patch using gauge symmetries, then that constructs a gauge bundle over the manifold, and this gives us the way of treating Yang-Mills theory. With a B field, we patch together using the B field transformations, and that gives another structure which is known as a germ. And however, string theory has got new symmetries not present in field theory, the dualities. And so there's the interesting possibility of using these new symmetries to patch together local patches to construct new kinds of geometries, although geometries is perhaps not the right word here. And these are some of the examples of what are called non-geometric string backgrounds. So, for example, in the context of T-duality, I talked about T-duality taking a large circle to a small circle. And so this would give a way of gluing a large circle to a small circle in a way where the physics was smooth, even though geometrically it would look horrible. It would look like there was a big and abrupt change there. So there's clearly new kinds of structures which could arise this way. And in fact, there's evidence that perhaps generic solutions of string theory are various kinds of non-geometric string backgrounds, and that the conventional geometries that we see in supergravity and so on are just the tip of the iceberg. So by probing some of these questions and trying to understand how string theory can incorporate these things, these are clearly things which can't be understood in the supergravity limit, because supergravity just gives the geometric backgrounds. Then one might, the hope is that it will give light, shed some light onto some of the nature of string theory. So some of the kinds of dualities which arise in string theory are the T-duality, which is the perturbative symmetry of strings compactified on the torus, or more generally on spaces with a torus vibration. And this arises in all string theories, bosonic and superstrings. There's the U-duality symmetry, which is the non-perturbative symmetry of the type 2 string theory compactified on the torus, or more generally on a torus vibration, a manifold with a torus vibration. There's mirror symmetry, which is the perturbative symmetry of the superstring on a Calabi-Yau manifold. And it's rather strange and peculiar that the symmetries we find are very specific to particular kinds of backgrounds. And one of the key outstanding questions is that of understanding whether or not there's remnants of any of these on more general backgrounds. One of the reasons why it's hard to see how that might happen is that T-duality, for example, maps changes momentum modes with winding modes. And on a general manifold, there may not be any winding modes at all if the space has trivial H1. And in that case, there wouldn't be, it's not clear what T-duality would do in that case, or whether there'd be, how it would attempt some kind of generalization. But nonetheless, each of these kinds of symmetries could be used in patching in the way I described to construct new kinds of geometries, T-folds, U-folds, mirror folds. But I'll be talking about just about the T-folds because they're the cases which are easiest to talk about because they can be treated within interpretive string theory. So for strings on a torus, the states are labeled by the momentum on the torus. So on a circular direction, the momentum is quantized. And also by the winding numbers, the number of times the string winds around each of the toroidal directions. And the string then gives rise to an infinite set of fields which depend on P and W. So in the case where it was in space-time, we just get a set of fields which depended on P. So in Minkowski space, it just depended on P. But because there's a torus, it depends on both P and W. And T-duality tells us that P and W should occur democratically. And then we could Fourier transform to a doubled space where the Fourier transform of P is just the torus coordinate x. And the Fourier transform of W gives the dual coordinate x tilde, which I mentioned earlier. And so this gives rise to an infinite set of fields which depend on these double coordinates. And this is what I refer to as a double field theory. And it arises from, we thought of as arising from closed string field theory. And it gives a strange kind of generalization of the field theory, which is necessarily intrinsic consequence of string theory. And it has some mild kind of non-locality in this double space, which again I hope to have time to talk about. And one could look for a finite subsector, perhaps of a metric, a B field, and a dilaton sitting inside this, and looking for a finite set of fields. And that will be these ideas will be the ones I want to explore in the third lecture. They give rise to a double field theory or the double torus, and the general solution of string theory will necessarily involve these kinds of double fields. And one of the reasons one of the motivations for this is the kind of framework which is needed for understanding some of the non-geometric backgrounds, the T-folds that I mentioned. And one of the things we'll see is that there's a real dependence on the full double geometry. These dual dimensions, these extra coordinates are not auxiliary or gauge artifact, and so the full double geometry is both physical and dynamical. So that summarizes that's an overview of some of the things I wanted to talk about. So the next part will be to turn to a more technical treatment of T-duality. But before doing that, maybe this would be a good moment to pause and see if there are any questions. So let's start by thinking about a periodic scalar. So we have a field, a two-dimensional field x taking values in a circle. X is identified with 2 pi r, with a radius by 2 pi r, so that there's some lives on a circle radius r. And so we have maps from the string to this one-dimensional space. So what I'm really thinking about is a product of Minkowski space with a circle. So there'll be some extra fields representing the motion of the string in the other directions. So if I'm talking about the bosonic string, there'll be one circular dimension and 25 Minkowski directions. But I just want to focus attention on this one field. And in the free theory, the two decouple. And I'll think about a cylindrical world sheet. So sigma is periodic with period 2 pi. And then if we expand out x to sigma and tau, this will satisfy a free two-dimensional wave equation. So it's got some pieces linear in the coordinates, plus an infinite set of oscillators coming from the zero modes, sort of coming from the Fourier expansion of x in sigma. And I'll write these out explicitly on the next slide. But for the moment, I wanted to concentrate on these constant pieces. This p is something which would be there for a particle and corresponds to the momentum. Because it's a particle moving on a circle, the momentum is quantized, and it's given by the units of alpha prime times n over the radius. And that's so that the wave functions involving e to the I of p dot x are well defined when you take into account that x is ambiguous modulo 2 pi r. And there's and as sigma goes from sigma to sigma plus 2 pi, we see that x goes to x plus 2 pi w. So if w is mr, that means that where m is an integer, that means that the string is wrapping m times around the x-dimensional circle. So here, n and m are integers. So we've got these two integers here, and then there's the oscillator pieces occurring there. So the two-dimensional wave equation has got a general solution, which is an arbitrary right-moving function of sigma minus tau, and an arbitrary left-moving function of sigma plus tau. And if we look at the full mode expansion, we have the linear terms which involved n and m, which are now combined into a piece proportional to sigma minus tau, with a PR which has got this dependence, and a piece proportional to PL, which has got this. So these are combinations of the n and m term, the momentum and winding we saw before. And then we have a Fourier sum of modes. So it's periodic in sigma, so we have, and it's a function of sigma minus tau, so it must have a Fourier decomposition of this kind, so we have some oscillators alpha, so Fourier modes alpha, and some Fourier modes alpha tilde L for the right moving, for the left moving. And then in the quantization of this, then one imposes, and so here we also have, there's also the center of mass coordinate x, the center of the string. And this we split into two, an x left and an xr, which are constant pieces. And then in quantizing the theory, one imposes conventional quantization conditions between PR and XR and between XL and PL. And each of these alpha L's become a set of, these alpha L's become an infinite set of harmonic oscillators where alpha minus L with L positive is an annihilation, it's a creation operator, and alpha plus L is an annihilation operator. And similarly, these also satisfy an infinite set of harmonic oscillator commutation relations. And the Hamiltonian has got split into a sum of a left moving piece and a right moving piece, which has got the sum of the relative momenta squared. It's got the momenta squared plus a sum, a normal ordered sum over the oscillator contributions, the left and right moving oscillators. And one can see that this Hamiltonian is invariant under the transformation which takes r over alpha prime to alpha prime over r, and it swaps m and n. And that's because if we look at here, we see that this is, if we swap n and m and replace, and note that this is 1 over this, so that taking this to minus itself and swapping n and m would leave, would change PR to minus PR, and would leave PL invariant. And because PR involves a square, PR squared, PR going to minus PR leaves this invariant, and PL going to PL leaves that invariant. And similarly, if we introduce, if we flip the sign of these oscillators with respect to these, this also leaves this invariant. So that what we have is, we have a transformation which takes, put it together, it takes XR to minus XR and XL to XL, which inverts the radius, takes R over root alpha prime to alpha prime, root over alpha prime over R, and swaps the momentum and winding, swaps the momentum N with the winding M. And here we see it's the symmetry of the Hamiltonian. It's also a symmetry of the partition function, because the partition function involves the sum of these momenta over all positive and negative values, satisfying the quantization conditions, and it involves L0, the two terms in the Hamiltonian which are invariant, plus the partition function of any other field, for example, the 25 extra fields, the 25 dimensional Minkowski space I've been suppressing. So the T-duality preserves the Hamiltonian and the one-weak partition function, so that it's a symmetry of the free spectrum, and it preserves the free spectrum. One can see that by looking at the mass squared of the term, so it involves terms like this, which is clearly invariant under taking R to 1 over R and swapping N with M. So this means that the theory on the large circle of radius R is physically equivalent to one on the small circle of radius alpha prime over R, where the momentum modes in this theory correspond to the winding modes in this theory, and vice versa. So if R is large, it means that the momentum modes are light, and the winding modes are heavy. Whereas in the dual circle, it's the winding, which is small, it's the winding modes which are light, and the momentum modes which are heavy. And we can rescale the fields by factors of R, so that X becomes dimensionless with period 2 pi, and we could use introduce the component of the metric to R squared and call that G11. We can rescale that to make it dimensionless, and then rescale R into units of root alpha prime, so that we end up with X, R, and G11 being dimensionless. Then the transformations in these units, so working units of alpha prime, string units, then just take the simple form where we take the metric to 1 over the metric, so the metric involves the R squared, and takes R to 1 over R. And this will be the kind of form which we'll be using in later slides. So the T-duality is a symmetry of the quantum string theory on the circle cross the Minkowski space. The quantum theory is a two-dimensional conformal field theory, and the space of these conformal field theories is labeled by this quantity R, the radius of the circle, which is the modulus of the theory. And so what we have is an isomorphism between the conformal field theory at the radius R and the one at radius 1 over R, where we're swapping momentum and winding and relating states in one space to states in the other space. And there's a missing minus sign in front of the one of the oscillators here. So we're finding that large and small circles are equivalent in this sense. We define X as the sum of X is the sum of the left moving and right moving pieces. We could define the difference as X tilde, and whereas the zero mode of X is conjugate to momentum, the zero mode of X tilde is conjugate to winding number. And the duality can be thought of as a transformation from X to X tilde, where X is the coordinate of the circle of radius R and X tilde is the circle of radius 1 over R. We can be thought of as a two-dimensional version of electromagnetic duality, where we're looking at where, if we think of X as a naught form gauge field, with field strength to the one form, dx, then we're changing that to the dual field strength, dx tilde, by these transformations. And we're swapping the field equations for X with the Bianchi identities for X tilde and vice versa. So it's like a two-dimensional version, equivalent of electromagnetic duality in form. And in doing this, we're swapping fundamental quanta, the momentum modes, with solitons, the winding modes, these are world-sheet solitons. And we're getting a new symmetry of the physics between the large radius and small radius. So it's a rather remarkable feature and something very different from what we're used to in conventional field theory. This extends to strings on a d-torus. If we take a kind of target space which is a product of a d-torus with periodic coordinates xi, then instead of having just a single radius for each x for a single coordinate, we've now got a constant metric on the torus, which incorporates all the radii of these circles and the angles between them, and a background V field, which will also take to be constant. These combine into a tensor which uses symmetric part as G and antisymmetric part B. And on this theory, we know that there's a set of large diffeomorphisms which are general linear transformations which act linearly on these tensors, but they have to preserve the periodicity conditions. So that means that you can only take integer-valued matrices, because otherwise it would take the transformations would not preserve the periodicity conditions. And these can be thought of as large diffeomorphisms on the torus. These form what is known as the mapping class group of the d-torus. You can also consider constant shifts of the B field. Those are symmetries of the theory, at least of the quantum theory, provided these shifts are integer valued. If they're integer valued, then the action changes by 2 pi I times an integer, including action. So e to the minus action is invariant, and so the quantum theory is left unchanged. Because the classical field equations only involve the curl of B, this is clearly also a symmetry of the classical field equations, although not of the classical action, which shifts the classical action by a constant. And also the inversions at each of the circles, and for each value, each circle we can take the radius to 1 over the radius. So we have these sets of symmetries of the theory, and one can show that they don't commute with each other, and that together they go to generate an infinite dimensional discrete group, and this group is ODDZ. So these are matrices. These are 2D by 2D matrices, where these are D by D blocks, which are in the group ODD and are also integer valued. And the action of this on these E's, where A, B, C, and D are these D by D blocks, is this fractional linear transformation. And it also acts on the momentum and winding, which lie in a two-dimensional lattice. So this ODD consists of rotations of lattice vectors, but nonetheless preserving the lattice structure. So that's why they're integer valued. There's another way of seeing why they must be integer valued. So you can also think of it as, if you look at the moduli space of conformal field theories on torus, it turns out to be parameterized by this coset space. So from this point of view, the moduli are G and B, and G and B, there are D squared degrees of freedom there. These fit into a D by D matrix, and this is a D squared dimensional coset space, and it turns out to be that G and B can be thought of as parameterizing this coset space, and this moduli space must be then identified under the action of this discrete group. So the T-duality map can be thought of as a map between equivalent realizations of the same conformal field theory, just as the diffeomorphisms would take you through different realizations of the same conformal field theory. conformal field theory, the same conformal field theory written with different coordinate systems would be regarded as physically equivalent. So, for strings on the D torus, I've been talking so far about the free theory, and there we've seen that there's a natural introduction of this variable x tilde conjugate to the winding number. But for example, in electromagnetic duality, introducing a magnetic potential, that's something you can do. It's often, it doesn't really have any content, and there's no, one can formulate the theory entirely usually with just one or other potential. But things are a little different in string theory. It turns out for the interacting theory on a torus, we need x tilde to play implicitly. We need x tilde as well as x to define the interactions. And that's because the vertex operators involve structures like this, which involve exponentials with some momentum times either xl or xr, the sum and difference of x and x tilde. And these occur asymmetrically, and so you need to have these separately. And so writing down the interactions automatically requires using both x and x tilde. And so they're an intrinsic part of the theory. And it's also seen in the second quantized approach in the string field theory, where the fields depend explicitly on the zero modes of both x and x tilde. And that suggests working with the double torus, where one has both of these sets of coordinates, which transforming linearly under ODDZ. And that will be the basis of the double formalism, which I'll be talking about tomorrow. So let's see. Okay, so I'm going to talk now about trying to understand in more detail. We talked about how the T-duality acts on a space which is just a torus times a flat space. But what happens more generally if you've got a curved manifold which has perhaps got a torus vibration, where the curved manifold has got some circles, and how does T-duality act in this case, in this way? And so and I'm trying to understand this, we're going to understand the T-duality transformation rules worked out first by Boucher many years ago, and understand in more detail about how the geometry and the topology changes as a result of duality. So what I'm going to do first of all is just give a quick and dirty version of the argument, which will have a lot of failings in it, and then but it's the version of the argument which is often given in talks and in the literature. Then I'll come back and criticise that and say what's wrong with that and try and put it right and try and look in detail about how these things should be done properly. So the argument I'm going to give sort of works in special cases, but I'll talk about what goes wrong with that. So let's suppose we've got a signal model which has got a metric, a B field, and a dilaton. And let's suppose that there's an isometry. What this means is there's a diffeomorphism which will leave the metric and the B field and the dilaton invariant. So suppose we choose adapted coordinates where we have the isometry direction is just x, so that the isometry corresponds to just shifting the x coordinate by a constant, lambda, so lambda is the parameter of the transformation, and leaving all the other coordinates y fixed. And suppose also that the metric, the B field, and the dilaton only depend on y and not on x. Then, because there's no explicit dependence on x, shifting x will leave these invariant. And so x only appears in this action through its derivatives. And the gradient of x will be left invariant by shifting x by a constant. And so that will be a symmetry of this theory. And this corresponds to an isometry in the direction x. So, suppose we wanted to promote this to a local symmetry where we included local shifts where lambda now depended on the worldsheet coordinate sigma. So you want to consider local shifts of x. Then to do that, one would also need to introduce a gauge field, as one would expect, which changes by the gradient of lambda. And then if we just take this action and minimally couple by taking grad x to grad x minus a and leaving grad y unchanged, then we'll end up with an action which is invariant under these transformations with lambda being local. And this is what's meant by saying that we're gauging the signal model. Now suppose we add a Lagrange multiplier term to the gauge nonlinear sigma model. So we introduce a new field which I'll call x tilde, and we have an integral of x tilde times the field strength of the gauge field f. So this imposes f equals 0, so that A is a flat connection. So locally, at least, that means that A is pure gauge. And so let me ignore sort of global issues for now. And that we could argue that we could use this to set A to 0. And setting A to 0, then the minimal couplings would just be reduced to the conventional couplings, and we get back the original model. On the other hand, we could get a dual sigma model by doing things in a different order. So A only occurs through this A and X only occur through this combination of grad X minus A. So A is an independent field, so we can shift A by grad X to absorb all the dependence of X in this Lagrangian completely. Or another way of saying that is we could use this gauge symmetry to gauge X to 0 locally, because X is an arbitrary function of sigma, and lambda is an arbitrary function of sigma, so I choose lambda equals minus X to gauge X to 0. So we could do that, and then X drops out. Then, if we integrate by parts, this becomes something which is dx tilde wedge A, and so we just have A appearing algebraically here, and we have each of the grad x's has been replaced by an A, so we get some A squared terms here, some A squared terms here. So A is an auxiliary field appearing algebraically. It appears just quadratically. We can integrate it out, and this will give a new sigma model for the coordinates x tilde. So here we've got some terms quadratic in A, we've got terms linear in A. So this will give terms quadratic in dx tilde when we eliminate A. And so we end up with a new sigma model for x tilde involving the coordinates x tilde and y, which will have new couplings, which will all be independent of x tilde, and will give new metric B field and dilaton, which arise in this way. So it's a simple calculation to work out what happens by integrating these out. And the transformation from the original metric B field and dilaton to these new ones are what is known as the Boucher transformations, and I'll give them explicitly shortly. So here we see a simple argument which takes a nonlinear sigma model, one gauges it, one adds a Lagrange multiplier term, then integrating out in two different ways gives two different, manipulating the same master theory in two different ways gives two dual sigma models. And so, starting off from the same master action with the gauge sigma model plus the Lagrange multiplier term, we could argue that the two models arising in this way must be equivalent, arising from the same theory. So what's wrong with this argument? So, first of all, the condition f equals 0 which implies A is pure gauge locally, only applies globally if the world sheet has got trivial first cohomology class, H1 of R. So it would be okay for a sphere, or a two-sphere, the world sheet was a two-sphere, but not for a cylinder or a higher genus Riemann surface, because each of those has got non-retractable loops. So one can't remove A to get back the original sigma model. So what it means is that even though f is 0, there can still be Wilson lines around each of the non-contractible loops. And so to specify the gauge field, one would also need to get rid of to be able to eliminate A, one would need to be able to argue that there were no Wilson lines. So in the original argument, one can't remove A to get back to the original model. One could get rid of most of the local degrees of freedom in A, but one still has the possibility of having non-trivial holonomies, non-trivial Wilson lines about closed circles, closed loops, closed cycles, closed one cycles in the target space. Sorry, on the world sheet. Next, the B field is the gauge field. And so in general, isometries which preserve the physics might only need to preserve B up to a gauge transformation, not to preserve B exactly. And this argument has not really used the fact that X is periodic, or that the dual X tilde is periodic. So it would seem to apply an equivalence even when you had non-compact isometry orbits, so that we're relating things which had either didn't have momentum modes, which didn't have winding modes. And what would happen if instead the isometry has fixed points? In that case, one can't choose adaptive coordinates in the way I said, and so none of that works. So one needs to do, although it's the base, what I've discussed is the basis for a good argument, it's not, this doesn't quite work. So what I want to do is now try and put that right. So the first thing is that instead of using X tilde F, we use something which differs from that by a total derivative, which is dx tilde wedge A, which looks a bit strange, and we'll understand the reason for that in a moment. But now, under large gauge transformations, this was manifestly invariant, but now under large gauge transformations, A is not invariant. And as we'll see in a moment, the Euclidean action on the Riemann surface will then change by 2 pi I times an integer, provided this scalar x tilde is chosen to be periodic. If we do that, then this shift will mean that e to the minus the Euclidean action will change by e to the minus 2 pi I n, and so will be invariant. And so the quantum theory will be preserved, even though under a large gauge transformation, this the classical action will change by a constant. And we'll also see that if x is a circle of radius r, the radius of the dual circle x tilde must be proportional to 1 over r, so that we're seeing that we get the T-duality relations coming from this from looking at large gauge transformations. And secondly, with x tilde periodic, will be a sum of a good periodic function with no winding, together with a set of functions, each of which would wind around h of gamma, where h of gamma has non-trivial winding around a one-cycle gamma. So then, because f is a good function, we could really integrate by parts here, and this is equal to minus f, little f times f. So f is a Lagrange multiplier, and we can use this to impose the constraint. And so varying with respect to f imposes the constraint f equals 0. And so before, with x tilde, we couldn't integrate by parts the way we did before with x tilde because of these parts here. But for the good function part, then one can. Now, integrating over h gamma over these, which involves summing over the windings of each and summing over the individual cycles h gamma, then imposes the holonomy of A vanishing on each cycle. So the integral over the line integral of A, the Wilson line around the cycle gamma equals 0. So we're seeing that by using this, we're getting two parts from this. We're getting one term which gives the f equals 0, but the winding modes of x tilde, integrating over the winding modes of x tilde will give the extra structure that it's imposing that the Wilson lines will vanish. And so with the Wilson lines vanishing, then it follows that the flat connection without Wilson lines will then be gauged to 0. So in this case, we could really get back to the original model by putting A to 0. So let's look at this in a bit more detail, and we'll get to the final form of the symmetry transformations. So let's look at the nonlinear sigma model on a Riemann surface. I've chosen units, I think, in alpha, which alpha prime is 2. And here, on a Euclidean space, there's a factor of I in front of the Wessel-Witten term, which comes from taking t to I tau to I tau. Because this is the Wessel-Witten term is linear in tau derivatives. Or if we use complex world-sheet coordinates, it can be written in this way. And a lot of the formulae will work also for Lorentzian signature worldsheets, provided that this is the left-moving derivative with respect to sigma plus tau, and this is the right-moving one with respect to sigma minus tau. The only difference being that the factor of I, there'll be some factors of I different in the Lorentzian signature. So, to be specific, I'll choose the Euclidean signature for this. Then the Wessel-Witten term can also be rewritten in terms of a three-dimensional integral. So here, if we choose a three-dimensional space sigma 0 of G, whose boundary is the Riemann surface sigma of G, so this could be thought of as filling in the Riemann surface to get a solid object, three-dimensional object. Then, if H is properly normalized, in other words, it's chosen to be representing an integral cohomology class, then a standard argument show that this will be independent of the choice of this three-dimensional, the way you're choosing to fill this in. But strictly speaking, this requires that the second cohomology of the target space is 0, because if it's not, then there is one can't in general choose a way of filling this in, whose image lies in the target space. So this is enough to fix the Wessel-Witten term, and so if H2 is 0, we can work with this form of the action instead of this. But if it's not, then we really need to use the two-dimensional form and be very careful about what we're doing. So suppose the target space is an isometry, so there's a killing vector k. So this was a vector pointing in the direction of the isometry. So here I'm not choosing particular adapted coordinates yet. So the Lie derivative of the metric is 0, and we suppose it also preserves h. Now the Lie derivative on a form always has this form that it's related to ikd plus dik. I learned at some of the seminars at the Wardita last week that this is called, earlier this week, this is called Cartan's magic formula. So I of k, I sub k means that you're acting on a 3 form by contracting it with the vector to make a 2 form. So acting with ik means you're contracting one index of the 3 indexes here with one index on the k to make a 2 form. And the term where the d hits the h is 0 because dh equals 0. So we get d of ik. So locally there's a 1 form in which we get ik. So this is closed, so locally it's d of a 1 form, v. And then we can work out what the Lie derivative of v is. And we find that it's given by using the dv equals h, we get this form. So as a result, we find that the Lie derivative of b is d of a 1 form, where this is given by this. So in other words, under a Lie dragging, b changes by a gauge transformation. So as I said before, the b field is not invariant, but it's invariant up to a gauge transformation. And as a result, there's a rigid symmetry of the nonlinear sigma model under which x changes by this, where epsilon is a constant. And, for example, the variation of the Wessel-Witten term involves the Lie derivative of h, and if you're imposing the Lie derivative of h is 0, then that variation is 0. So you have a rigid symmetry, so there are conserved currents, and these take this form. And we can now attempt to gauge this isometry by now promoting the parameter epsilon to being a function of sigma. And as a result, so we introduce a gauge field whose transforms by the derivatives of epsilon. And then we add the variation of the classical action involves the Noether currents times the derivatives of the parameter, as you'd expect. And we could cancel by adding the Noether coupling of the currents to the gauge fields. But now when we look at the variation of this, we find that the variation of these j's gives another transformation. So this gives something whose the variation of s prime is 0. And part of this can be cancelled by adding a term like this, where k squared is the norm of the killing vector with respect to the metric g. And when we add all these things up, we find that the variation of these three contributions to the action add up to give a transformation of this kind. And so we see that this is only invariant if k dot v equals 0. So in other words, there's an obstruction to gauging in general. Gauging is only possible if two things are satisfied. First of all, that k dot v equals 0, and secondly, that v is globally defined. We knew that ik of h is exact, is d of some v, but in general, this v would only be defined locally, and we'd need a globally defined v to write down the gauging. And one could see that by looking at the three-dimensional form of the gauged action, which involves minimal coupling of the h field, replacing dx by the covariant exterior derivative, and a term which explicitly involves this vector vi. So this to be a covariant expression, as it should be, and requires that v be a well-defined one form on the target space. So the gauging is only possible if these two are satisfied, and if not, then there is an obstruction to the gauging. But there's a way around these obstructions by introducing a new field. Let me call it chi for now. This will be the field I was calling x tilde before. And if we introduce one that transforms into something proportional to k dot v, so going back to this is part of a general story where gauging nonlinear simple models with Wess-Zumino terms is not possible in general. There are obstructions to that which are related, which have got an interesting topological interpretation. But now, if we look at this variation, we can cancel this by adding this. The variation of this will cancel this variation with this variation of chi. And then we find that the invariant action we get is by adding all these up takes this simple form. So maybe I should stop now. So I'll continue the discussion. So what I'll do, I'll start off tomorrow by finishing the discussion of this. So what I'll show is that I'll explain the meaning of this invariant action and the topological and the geometric meaning of this extra coordinate chi. And given this form of the action, I'll show in detail the things I claimed earlier about the invariance under large gauge transformations, fixing the periodicity of chi, and I will show that, as claimed, that integrating taking this master action, dealing with it in two different ways, will give rise to two different dual sigma models. One the original sigma model, and one the dual sigma model. And so I'll finish that part of the argument tomorrow, and I'll stop there for now. Thank you.
Any short questions for Chris? No short questions.
Any more questions?
Okay, so let's thank Chris again. We have a break.